Okay, so now we want to talk about the idea of a graph being planar. So a graph is planar if it is possible to draw it on a flat sheet of paper such that no edges cross each other. So this possible matters a lot. So if you guys remember, we have two different ways of drawing K4. This guy, we actually have more than that. No reason that we have to restrict our edges to being straight lines. Let's just I can connect them like this as well. So this guy is a planar drawing, this guy is a planar drawing, this guy is not a planar drawing, but K4 is a planar graph because it's possible to draw it on a flat sheet of paper such that no edges cross each other. And how do we know this? Well, there's one thing is we can just straight up draw it and see. But we do have a general characterization of graphs that look like this. And that, again, is thanks to Euler and his formula. There's a bunch of different Euler's formulas, but this one is the one that we will talk about in the context of graph theory. So that's F plus V is equal to E plus 2. This is the number of faces. So in this case, right here, we have 1, 2, 3, and then we also have the outside face. So we have 4. The number of vertices. So here we have 4 vertices. And then edges, we have 1, 2, 3, 4, 5, 6 edges, plus 2. So if it is a planar graph, then it satisfies this. And we can check that this applies here. So we have 4 faces, 4 vertices is equal to 6 edges plus 2 as our default number there. So this checks if it's possible to write it out like this. So one place where you might care about this is if you want to describe a circuit board. Any graph that represents those circuits must be planar, assuming that is a single board and you're not jumping between several boards. So that is one reason you might care about the planarity of a graph. So another thing to note is that a planar graph, another characterization of it is a planar graph is a graph that does not have K3 or K5 as a minor of it, as a graph minor. So this obviously requires us to define what a graph minor is. A graph minor is a graph that can be achieved via any combination of 3 processes. So edge deletion, vertex deletion, which deletes any edges that are attached to the vertex, or edge contraction. So if I have little bow tie graph here, and I contracted this edge, then what I would get in the end is this. Contraction. So that is an alternative characterization of the planarity of a graph. There are generalizations of Euler's formula. So basically, if I were allowed to look at everything on a donut here, instead of on a flat sheet of paper, then I would have more freedom. If I were to look on a double donut, then I would also have more freedom. And then in that case, this number goes down. So I think on a donut, or a torus, as we like to call it in math, we just get rid of that 2. And then if you have a double torus, it's -2. If you have a triple torus, it's -3, on and on. You can draw it. That tells you how you can draw it without any edge crossings.